Hi, today we're going to study chapter 26, relativity. Relativity, we have classical relativity and Einstein's special relativity and general relativity. So we'll discuss some detail later. And the special relativity study motion at constant speed. Uh, that means you can go very fast, close to speed of light, but must be a constant, not acceleration. Uh, Now the general relativity deal with the accelerated motion uh, when velocity can change, and also discuss the theory of gravity. Uh, so we're going to concentrate to special relativity only. Okay, 100 years ago, end of 19th century and beginning of 20th century, scientists find something must be changed. For example, Newtonian mechanics, like we studied Newton's law. Okay, it's limited uh, only for low speed. Low speed. Uh, Low speed include everything we study every day, except a motion at a very high speed, close to speed of light. Let's say at least 10%. That's a very high speed. Uh, so now, section 1, we're going to study principle of relativity. Okay, classical relativity, also called Galilean relativity, uh, which state a law of mechanics are the same in all the inertial frame of reference. Uh, so note the inertial frame of reference. That is the motion at a constant speed. For example, we stand on the ground, Earth's surface, and someone goes straight line motion at a speed, like inside of airplane. The speed must be a constant speed. So we call the inertial frame of reference. So now the law of mechanics are the same in all the frame. For example, if you stay inside uh, and your classmate stand on the Earth's surface, uh, so you throw something up and down, straight up, straight down. Uh, so come back at the same location. But your friend will say, when you throw something up, uh, because the airplane go forward, so up and down at a different location. Uh, Same location to you and different location to someone observed on Earth's surface. So who's right? Both. Because you are both in the inertial frame of reference. Uh, okay, you agree something, for example, you agree the time goes up and back is same as he measured. Uh, okay, so from here to there will take same time. And we're going to study, when we study the special relativity, you're going to find even the time is not the same. Okay, so that we call classical relativity. Uh, so now we have a problem when we study very high speed, very high speed. So now let's say the classical relativity. Uh, okay, so only for mechanics, it does not apply to electricity, magnetism, optics, and other areas. So that's a problem. For example, when you add two velocity, we call addition law of velocities. Say you have an airplane, assume uh, go straight line, constant speed, speed is constant, 800 mile per hour. Then send out missile, same direction, at 200 mile per hour. So now, if you measure speed of missile, okay, from the ground, you're gonna find speed of the missile equals 800 plus 200, so the 1,000 miles per hour. So we use this equation. So this is speed of missile, this speed of missile from the airplane plus speed of airplane. But now this equation doesn't work when you measure speed of light. For example, we have to assume we're high speed. This train, the speed of train equals, let's say, 1%, 10%, let's say, of speed of light. Remember, speed of light is 300 million meter per second. So this 10%. So now, if someone turn on the light inside of the train, so what are we going to measure speed of light from here? Is the same or is higher? Okay, so the 3 10 to the power 8 plus 3 times 10 to the power 7 all still equals the same value. Okay, so all the experiment, scientists try again and again, all the experimental results tell us same thing. The speed of light, no matter how you measure it, always give you same value. 3 times 10 to the power 8 meter per second, or 300 millimeter per second. Never change. So that's a problem. Okay, so we have some very famous scientists, Michelson Morley experiment, this most famous one, and he proved speed of light never change in vacuum. In vacuum always equals this value. Okay, so now that's a problem we have the answer. So Einstein gave a principle of special relativity about 1905, and 10 years later, he also published the general relativity. Okay, so the whole theory of special relativity based on two postulates. Based on two postulates. Okay, Einstein said like, okay, if you agree these two, I tell you what's going to happen, like a Back to Future. If you do not agree, you have to prove I'm wrong, because in science we only believe evidence. Okay, so here's the two postulates. First one, the principle of relativity. This is modern, the Einstein's relativity. So this principle tells us all the physics law, not only mechanics, any law of physics are the same in all the inertial frame. So physics law must satisfy in different frame. I will discuss more detail. So physics law must be same in all the frame of the reference. Well, of course, there must be inertia. There must be at constant speed. Speed must be constant. Now the second one tells us speed of light in vacuum is universal constant. We're not going to change. Regardless of the velocity of the observer or velocity of the source of the light. Okay, so this tells us what happens. Suppose you have a flashlight lamp, a flashlamp. Okay, so this lamp fly at a certain speed. Let's say 20% of speed of light. Okay, then turns on. So now, if you measure speed of light, what do you find? 3 times 10 to the power 8 meter per second. So now the same lamp fly away from you, go that direction. See, go that way also. Let's say 20% of speed of light. Then turns on. Now you measure what you got, the same. So speed of light still equals 3 times 10 to the power 8 meter per second. Now, if fly this way and you following, you write on space shape, for example. Then you measure it, give you same thing. It doesn't matter which way you measure, the speed of light is a universal constant. So that's the two postulates. All the physics law must be same to everyone. Then the speed of light never change. Okay, so now for last 100 years, many science tried to prove Einstein was wrong, but every time they prove Einstein was right. So that's why we believe it. Okay, so now we're going to discuss some conclusions. So if we accept the two postulates, physics law are same to everyone, speed of light is a universal constant, let's see what happens. The first experiment, suppose we have two students. One stay inside of the train, the vehicle, will go very high speed. Another one stand on the ground. So now from A to student and from B to student the same distance. Also A prime, that's inside the vehicle. And B to this student also same distance. So now suppose we have the two lightning bolt at the same time, exact same time. Okay, strike on A prime, and B prime at the same time. Okay, so we assume these vehicles were very long. So take time for light reach to the two students. Okay, and at the same time, the trains go forward at a very high speed. Again, let's say 20% speed of light. So now, first of all, the student on the ground, she will see the two light come this point at the same time, right? Because same distance and speed of light is constant. So she believes these two events happen at the exact same time. At the same time, strike A and B. But for student inside the vehicle, it's different because travel this way. Remember, the B prime was here, so it's a shorter distance. And remember, A prime was over there, so travel longer distance. So the light travel this long, and this light travel only this long. Of course, this one will reach this student first. Okay, and he thought, well, this happened first from B prime, and this happens later because travel longer distance, and both light have same speed. See, so that's called the simultaneity. Okay, so the simultaneity to one person, but not to another person. They do not agree, times the same. Okay, think about this. So now, even more interesting, we can study time dilation. Okay, so now, again, we choose a vehicle. Assume this vehicle can go at a very high speed, let's say 20 or 30 or 50% of speed of light. Inside, we have one student, then outside another student. I'll give a name. It's called Mary and Ben. So Mary turn on the laser. So laser goes up, reflect from mirror, and come back, and come to the detector. So Mary measure the time. So the light go up and down. So distance D, another D, so 2D, 2D. The speed of light, well, we know, is constant. So she measures time. So now, because this vehicle goes so fast, Uh, so the Ben gonna see something different. Uh, because when the light reaches the ceiling, uh, the mirror is not there anymore. It go forward to there, uh, then reflect back, and the vehicle still go forward. When the light come back to Mary again, well, Mary is over there. See, so for Ben, the light travel up, down, that way, like a triangle. Okay, so this distance, of course, see, go up this way, down that way. So this distance, up and down, is longer than uh, this distance, straight up and down. Okay, so Mary and Ben uh, think the light travel different distance. Uh, this is for Mary, and this is for Ben. But they both agree speed of light is constant. So of course they will think the light travel different time. Longer distance need more time. So now we're going to calculate. So now let's see this triangle. So Mary sees the light go up and down, back. Now Ben say light go this way. So this distance, of course, okay, travel at speed of light. Okay, so half delta t, because total time from here back there is delta t. Uh, from here to the ceiling is half. So speed of light times half delta t. That's like travel from Mary's hand to the ceiling, the mirror. Okay, now same time the vehicle go forward, travel this long. That's speed of vehicle v times half delta t. Okay, so now this distance, of course, is the from floor to the ceiling. So now we're going to calculate, see what's the difference. So to observer in vehicle, that's for Mary. The time is 2d divided by c. That's total distance up and down, then divided by speed of light. Okay, so this time we call delta TP. This is measured by Mary. Okay, so now Ben gonna see like that. Okay, so now we're gonna calculate this one here. The delta T. Delta T is measured by Ben. Okay, so now see this triangle. Of course, we know this square plus that square equals that square. Okay, so this square, that's a c half delta t square equals this part square. That's v square times half delta t square. Then plus d square, right? We understand this part. Square plus that square equals that square. Okay, so now we're going to solve this. The first thing we're going to move, okay, this term to the left. Okay, so half delta t squared is the same. So we have c squared minus v squared, I'll use parentheses, times half delta t squared. Delta t is time measured by Ben, observer on the ground, equals d squared. So now we square root. So we square root, and this square cancel, so we have this, right? Square root give you that. Okay, so now we times 2 both sides, divide the square root both sides. So we find the delta t. So delta t equals 2d divided by square root. So now we take the c outside. Okay, so it's very straightforward. So, okay, for example, this one here equals c squared times parentheses 1 minus v squared divided by c squared, then close, right? Okay, Then you have c squared come out, become c. Okay, then we have 2d over c times 1 over square root inside of 1 minus v squared over c squared. Again, v is speed of vehicle and c is speed of light. Okay, so now look this one. Delta Tp, that is time measured by Mary, equals 2d over c. So we substitute this one for that term. So we're going to find delta t, the time measured by Ben, equal delta Tp, measured by Mary, divided by square root 1 minus v squared over c squared. Okay, so now we write this part, that part together. This is the final equation, very important. We call time dilation. So of course, inside the square root, always smaller than 1. So delta t p divided by something smaller than 1 will give you bigger number, right? So if you divide by 0.5, so this doubled. Divide by 0.3, it tripled. Divide by 0.01, so this is going to be 100 times. So anyway, so sometimes you write this way. So 1 over square root we call gamma, which is always bigger than 1, because 1, this is always smaller than 1. So 1 divided by this term, square root, always bigger. Sometimes we use this. So then time dilation become like this one. Delta t equals gamma times delta Tp. So now we have very important definition. So delta Tp, we give a name we call proper time. So that's the meaning of the P, proper time. So what is proper time? Who measure proper time? So proper time is a time interval measured by someone who see the two events at the same location. See, Mary sees the light go up and down at the same location. So Mary, inside the vehicle, measure proper time. So her time measurement is proper. Okay, because look at this figure again. So Mary sees the light go up and down at the same location. So her measurement is proper time. So now Ben sees the light go up and down at a different location. So his measurement is not proper. The time is not proper. Okay, so it's very important. So we're going to review later. You have to know which one is proper. The proper time is a time measured by someone who see the two things, two events happen at the same location. So now the proper time always shortest time. Other measurement always longer, always longer. For example, let's say this example, if you have a textbook, okay, on page 905. Suppose we have a pendulum on Earth's surface. A pendulum has time period equals 3 seconds from the Earth's surface. And what is the time measured by someone inside a spaceship, which is moving at 0.95 c, or 95% speed of light. By the way, we always use this kind of unit, 0.8 c, 0.75 c, 0.65 c. We always use c as a unit. You will say why. So now we're going to use that equation. We're going to use this one to solve it. Okay, so the delta t equals delta Tp, the proper time, divided by, well, square root. Okay, we're going to do that. For this problem, the 3 seconds is proper. because on the Earth's surface you see the pendulum go back and forth. See, start from here, go another side, come back at the same location. Okay, so that measurement 3 seconds proper. Now the space shape travel at 95% of speed of light. Okay, so now we just plug in. See that equation. Proper time divided by square root. 3 seconds divided by square root 1 minus 0.95 square. C square cancel, right? Because this has C. When you square, that is 0.95 square and C square. Divide by C square, so C square cancel. So now you have 3 divided by square root 1 minus 0.95 square. Okay, so if you use a calculator, let's see what we have. Okay, so we have 3 divided by, okay, square root. Okay, so inside we have 1 minus 0.95, don't forget square. Then you close parentheses. Okay, so you find what? 9.6 seconds. If you keep 2 digits, right? See, the proper time, okay, when you measure from the ground equals 3 seconds. Now, from the spaceship, you measure is 9.6 seconds. At 3 times longer. This is example. We're going to have homework and also some exercise later. Now, is this true? Has time really changed? Well, in daily life, we don't see this happens because our speed is too slow. Okay, let's go back here again, see Mary. So now if this vehicle travel at, say, the speed of the airplane, 1,000 meter per second, you don't even see this happens because it's too fast. Okay, light go up and down. You cannot see this kind of change. This only happen at a very high speed. So now we do have evidence. For example, scientists build this we call accelerator for particle physics. They measure half-life of atoms. You know, some isotopes has half-life. Okay, so now when those isotopes, the atoms, travel at a very high speed, close to speed of light, the time is going to change. So we do have evidence, but only the teeny particles can go that fast. So that's why we don't see the time dilation in daily life. Okay, so now 1971, two American scientists perform experiment. Okay, so they fly inside of airplane and measure atomic clock around Earth. So now they find at even speed of airplane, you can find a time change. But of course, the order is only a few nanoseconds. So we do have evidence for that. So now the next part, we're going to study how the distance change. So we're going to cover this part next class. Thank you.